Good morning, all of you. Welcome to Sri Jayendra Rank Zone. So, in the previous session, that is periodic table, we have done up to electronegativity. So, periodic properties we have discussed. Now, in this class also, we'll discuss more periodic properties. Now, what is electronegativity? So, already we discussed what is electronegativity. It is a tendency to accept the shared pair of electron towards itself. The tendency of an element to accept the shared pair of electrons towards itself is called electronegativity. And electronegativity of elements increases along the period while decreases down the curve. This also we have discussed in the last session. So what are the measurement by which we can do about electronegativity means that is electronegativity scales. So what are electronegativity scales? So that will give you the value of electronegativities. Some arbitrary scales for the quantitative measurement of electronegativities are as under. First we have Pauling scale. So what is Pauling scale and what is a electronegativity value, how to find it? It's very important for objective point of view. You have to remember these formulas. All the formulas are important. So if XA and XB are the electronegativities of atoms A and B respectively, suppose we are going to calculate two electronegativities of two elements. So if X of A and X of B are the electronegativities of atoms A and B respectively, then 0.208 root delta AB is equal to XA minus XB if XA is greater than XB. Root delta AB is outside. It is not inside. It is root delta is only square root for delta only. So root delta AB. Root delta AB outside is equal to electronegativity of A minus electronegativity of B if electronegativity of A and is greater than electronegativity of B. Our delta AB is equal to 23.06 XA minus XB whole square. Or simply what is delta AB is equal to nothing but change in electronegativity is equal to E of A minus B, E of A minus B experimental minus E of A B theoretical. So where EAB is the energy of the AB bond, EAB is the energy of the AB bond. Anyway, E of AB because it is single covalent bond AB. In a purely covalent molecule AB, the experimental and theoretical values of bond energy AB are equal. So delta AB is equal to 0. By this we can say XA is equal to XB. This formula only will apply in the examination. The first formula. Remaining all formulas just they have equated, but it is not important. Next, in an ionic molecule AB, if it is ionic molecule, for example, covalent molecule, we have to calculate like this. Whereas ionic molecule means like sodium chloride. So ionic compounds AB, EA, E of AB, energy of AB bond length is more than energy of AB theoretical. Experimental is more than theoretical. So Pauling assumed the electronegativity value of fluorine to be 4 and calculated the electronegativity values of other elements from this value. So the highest electronegative element in the periodic table is fluorine and its value is equal to 4. Its value is equal to 4. I hope it is clear. So fluorine electronegativity value of fluorine is highest. So most electronegative element is fluorine and most electropositive element is cesium. So the electronegativity value of fluorine is calculated as 4 and it is compared with all other electronegativity values. Next. So one more scale, that is Mulliken's electronegativity. So it is equal to how to calculate electronegativity value. Electron affinity minus ionization potential by 2. So if you do electron affinity minus ionization potential divided by 2, then both are expressed in electron volts. We'll use the formula electronegativity as like this. Next scale is Alfred-Rocho's electronegativity. So it is the distance between the circumference of the outermost shell and the nucleus is R and the effective nucleus charge. If the distance between the circumference of the outermost shell and the nucleus is R and the effective nuclear charge is Z, then Z effective is equal to Z effective E square by R square, that is equal to constant value 0.359 Z effective by R square plus 0.744. These are the constant values, where Z is called the actual charge present on the nucleus, that is number of protons, and sigma is called shielding effect. So these are only formulas we have to refer. No need of application of these formulas. Just application of formula only Mulliken's and Pauling scale only. So Mulliken scale, how to calculate electronegativity. Electronegativity value they'll give, ionization potential value also they'll give. So we have to do that nothing but difference of electronegativity minus ionization potential by 2. So these two formulas only will apply in the examination, competitive exam. So I hope it is clear now. Now the factors affecting the magnitude of electronegativity, atomic radius, as usual, effective nuclear charge, oxidation state of the atom, hybridization state of atom in a molecule. So this oxidation state and hybridization state we'll discuss in the next chapters. But the thing is, only you have to remember the variation, that is the trend in oxidation state as well as hybridization. So what is this oxidation and what is this hybridization? We'll discuss in chemical bonding topic. So atomic radius, as the atomic radius of the element increases, the electronegativity value decreases. So it is very important. So when compared to atomic radius, as the atomic radius of the element increases, that's why down the group electronegativity value decreases. So down the group electronegativity value decreases, and across the period atomic radius decreases, so electronegativity increases. So you have to compare all the properties. Next, effective nuclear charge. The electronegativity value increases as the effective nuclear charge on the atomic nucleus increases. So what does this mean? Here, as the nuclear charge increases, the electronegativity value also increases. Next, oxygen state of the atom. The electronegativity value increases as the oxygen state, that is number of positive charge of the atom increases. As the number of protons increases, automatically nuclear charge increases. As the nuclear charge increases, oxygen state of the atom also increases. As the oxygen state of atom increases, so automatically electronegativity value also increases. Next, we have hybridization state. So if the S character in the hybridization state of the atom increases, electronegativity also increases. If the S character, so we have sp3 hybridization, sp2 hybridization. So in sp3 hybridization, S character is less. sp hybridization, S character is more, because sp hybridization 50% S character, 50% P character. So this hybridization topic we'll discuss in chemical bonding. Just you have to remember these 4 topics, and atomic radius, effective nuclear charge, oxidation state, and hybridization state of the atom in a molecule. So these are effect of factors affecting magnitude of electronegativity. Next periodic property is valency. So far we have discussed 4 periodic properties. One is atomic radius, ionic radius, and covalent radius coming under same. Second is ionization potential. Third one is electron affinity, and fourth one is electronegativity. Now fifth one we are going to do, that is valency. So what is valency? Means the number of atoms present in the valence shell of an atom is called its valency. So it is a number of univalent atoms which can combine with the atom of other given element. This is the definition. Number of univalent atoms. Univalent means monovalent. Monovalent means valence is 1. So which can combine with the atom of other given element. For example, aluminum chloride, AlCl3. It means here univalent atom is Al is not univalent, but Cl3 is univalent. So how many chlorines are combining with aluminum? 3 chlorines are combining with 1 aluminum. So that's why valency of aluminum is 3. So in that way we can calculate. But anyway, for simple understanding, we can say number of valence electrons in the outermost shell is called valency. So valency is given by the number of electrons in the outermost shell. This point is most important. So if the number of valence electrons is less than or equal to 4, means for example, if an element has only 1 valence electron, 2 valence electron, 3 valence electron, or 4 valence electron, so its valence is also equal to 4. 1, 2, 3, 4 respectively. Means what? For example, if an element has 1 electron in the valence shell, its valence is 1. That's why sodium valence is 1. Similarly, if an element has 2 electrons in the valence shell, so the valence is 2. So that's why magnesium valence is 2. Similarly, if an electron has 3 electrons in the valence shell, its valence is 3. And if an electron has 4 valence electrons, its valence is 4. Like in the case of carbon. Carbon has 4 electrons in the valence shell, so valence of carbon is 4. Similarly, if the number of valence electrons is greater than 4, means 5, 6, 7, or 8, then valence is equal to 8 minus number of valence electrons. So how we got 0 group elements? Because their valence is 0. Because 8 minus 8. Because all noble gases, that is helium, except helium, neon, argon, krypton, xenon, and radon, except helium, all valence electrons, they have 8 valence electrons. That is, for example, neon, if you take 1s2, 2s2, 2p6. So it has 2s2, 2p6, 8 valence electrons. as they have 8 valence electrons, their valence is calculated as 8 minus 8. 8 minus 8, it is equal to 0. In that way, we got 0 group elements. So I hope it is clear now. So how to calculate valency? Valency up to 4, it is equal to the same, and greater than 4 valence electrons in an atom, it is taken as, that is 5. If suppose if an atom has 5 valence electrons like sulfur or phosphorus, phosphorus has 5 valence electrons in the outermost shell. So phosphorus valence is 8 minus 5. 8 minus 5, so it is equal to 3. That's why we got the compound called PCl3. I hope it is clear now. Now, many elements exhibit variable valencies, particularly transition elements. They have variable valence. They do not have only one valence. They have more than one valence. That is called variable valencies, and actinoids usually. So variation in a period increases from 1 to 4, and then decreases from 4 to 0, and moving from left to right. Variation in a group, no change in the valency of elements on moving down the group, because group the elements which are kept in the groups are based on their valencies only. If they have similar valencies, then only they will form a group. For example, first group elements they have valency 1, second group elements they have valency 2, third group elements they have valency 3. It means nothing but what? So group is nothing but valency. Based on valency only group has been decided. So there is no change in valency in all the groups. Means within the same group there is no change in valency. They have same valency. All the elements will have same valency, but atomic size and all difference, electronegativity difference will be there, but only valencies remain same. So there is no change in the valency of elements on moving down the group. All elements belonging to a particular group exhibit same valency. So for example, if we take first group elements, lithium, sodium, potassium, rubidium, cesium, and francium, they have valency only 1. Second group elements like beryllium, magnesium, calcium, strontium, and palladium, they have valency 2. Third group elements, they have valency 3. Fourth group elements, they have valency 4. Fifth group elements, they have valency again 3. Because number of valence electrons is 5, but the valency should be taken as 8 minus 5. 8 minus 5. So for example, fifth group elements, what are the fifth group elements we have? That is 15th group. We have nitrogen, phosphorus, and so on. So nitrogen valence is 3. It is not equal to 5, because it has 5 valence electrons. The configuration for nitrogen is 1s2, 2s2, 2p3. So nitrogen atomic number 7, 1s2, 2s2, 2p3. So it has 5 electrons in the valence shell. Even though it has 5 electrons in the valence shell, its valence is taken as 8 minus 5. It's not equal to 5. So there is no valency beyond 4. 4 is the highest valency of an element, which can combine with other element. So I hope this is clear about valency. Next. And based on the valency, we can write the formula of a compound. For example, I'll write a question here. The same question has come in objective. A question I'm writing here. A compound AB is formed by AB compound. AB compound is formed by two elements. A and B is formed by two elements. A and B. If A has 3 electrons in the valence shell, and B has 6 electrons in the valence shell. 6 electrons in the valence shell. What is the formula of the compound? What is the formula of the compound? So what is the formula of the compound? Now, if you see this question, this type of questions has come for objective. So AB is a compound formed by two elements, A and B. If A has 3 electrons in the valence shell, so if an element has 3 electrons in the valence shell, its valence should be taken as 3. So A is equal to 3. And B has 6 electrons in the valence shell, so greater than 4. So B valence should be taken as 8 minus 6. 8 minus 6. So B is equal to 2. So by crisscross method, A3, B2. So formula of the compound is A3, B2, and crisscross method you have to take file writing. So it is A2, B3. The formula of the compound is A2, B3. They will give options A3, B2 also, but you have to take A is 3, B is 2, crisscross method. If there are any common factors, we can divide that. But since 3 and 2 do not have any common factors, so answer is A to B 3. So in this way. Now number of valence electrons in the group, it remains same. If you see first group, second group, third, fourth, fifth, sixth, seventh, eighth, the valence remains same. For transition elements, they have variable valencies. That's why they are called as transition elements also. They have variable valency. They do not have one valency. They have variable valencies. So it is not only one particular. For example, iron can exist in +2 state as well as in +3 state. So +2 state it is called ferrous and +3 state is called ferric. Similarly, tin, Sn+2, Sn+4. So +2 state is called stannous and +4 state is called stannic. So transition metals only will have variable valencies, whereas Sn p block elements will have only single valency. So, and their valencies can be calculated by using, if they have 4 electrons in the valence shell, up to 4, their valence is 1, 2, 3, 4 respectively. Suppose if they have 5, 6, 7, 8 electrons in the valence shell, their valence should be taken as 8 minus 5, 8 minus 6, 8 minus 7, 8 minus 8 respectively. I hope it is clear now. Next. Next characters, metallic character of an element. So what are the metallic characters we have in the periods and groups, or how the metallic character changes? So that is the sixth periodic property, that is metallic character of an element. Metals have the tendency to lose electrons. Already we know metals contains free electrons, so they have the tendency to lose that electrons by giving some ionization energy. So larger the size of atom, more easily it would release the electron and thus would show high metallic character. So if you see in the first group, you have lithium, very small atom, because its size is very small because atomic number is 3. Whereas cesium, its atomic number is large, so it has big atom, so its size is small. So larger the atom, size of the atom, more easily it would release the electron, and thus it would show high metallic character. So in between lithium and cesium, which is highly metallic, cesium is highly metallic because it can lose the free electron very easily when compared to lithium. How it is losing an energy? Because by giving some ionization energy. So for both lithium and cesium will give ionization energy, but the ionization energy in case of cesium is less, because as the atomic size increases, the attraction of the center of the nucleus, that means the nuclear attraction to the outermost electron is less. So due to which what happens, it's easy to remove the outermost electron. Suppose if the outermost electron is under the influence of nuclear attraction, greater influence of nuclear attraction, then it's very difficult to remove that electron. So for that, more ionization energy is required. So electropositivity or the metallic character decides about the losing of electron. If a metal loses electron instantly by giving small amount of energy, we can say it is highly metallic in nature. That's why as we go down the group, the metallic character increases. As we go down the group, the metallic character increases. Means sodium and cesium, which is more metallic in nature, cesium. Like that it has. So sodium and lithium. Sodium is having more metallic character. Next, by this what we can say, metallic character increases down the group due to increase in size of atom, and metallic character decreases along the period due to decrease in atomic radius. So across the period, if you take from left to right in the period, what happens? The atomic radius decreases. So atomic radius decreases, and so metallic character also decreases. So metallic character is in turn depending on atomic radii. If the atomic radii is more, electropositive, that is metallic character is also more, because more easily we can remove that electron because it has less nuclear attraction. I hope it is clear now. Next, as we move from left to right, the metallic character decreases because the atomic radius also decreases. Next, non-metallic character is directly proportional, that is directly related to electronegativity, and metallic character is inversely related to electronegativity. Means simple it is. Non-metallic characters are nothing but they have electronegative nature because they gain electrons, and metallic characters they lose electrons. So that's why it is inversely related to electronegativity. Next, non-metallic character increases across a period and decreases down the group, whereas metallic character decreases across a period and increases down the group. So non-metallic character decreases along the period, and non-metallic character and metallic character. So actually here it is wrong given. Non-metallic character increases along the period. Non-metallic character, as we move from left to right, it increases along the period, and metallic character decreases. And down the group, metallic character increases, non-metallic character decreases. So you can change the sentence. Non-metallic character increases across the period, not down the group. You can change the sentence here. I'm writing here non-metallic character. Just I'll erase everything now. I'll tell you the statement. Here it is given wrong. Non-metallic character increases across the period. It is not down the group. Across. You can cut this. Across the period. You also should change in your classworks. Across the period means from left to right because metal changes to non-metals. And non-metallic character increases down the across the period. Non-metallic character decreases down the group. Here decreases is correct only, but you have to write not along the period, down the group. Just it is reverse. So always it is very confused. So better you practice notes. So down the group, non-metallic character decreases and metallic character increases. This is why all the metals are present on the left while non-metals are present on the right side of the periodic table. So I hope it is clear now. Next. Non-metallic character of an element. Non-metallic elements have strong tendency to gain electrons. So the non-metallic character is directly related to electronegativity. The electronegativity of an element is high, it is non-metallic in nature. If the electropositivity of an element is high, it is metallic in nature. So, and metallic character is inversely related to electronegativity. So already we know that metallic character is inversely related to electronegativity and non-metallic character is directly related to electronegativity. It means directly proportional. Across a period, what happens? The electronegativity value increases, hence non-metallic character also increases. Here it is correct only. The previous slide it was given wrong, that's why I have changed it. Now it is correct. Across a period, what happens? The non-metallic character increases and metallic character decreases, and down the group, electronegativity character decreases, hence non-metallic character decreases, and metallic character increases. So all these things you have to remember because they'll ask the trends of periodic properties in the examination, either decreasing order or increasing order. That's why it's very, very important. Now, if you see the diagrammatic picture, so metallic character, so increasing metallic character left hand side, increasing non-metallic character right hand side, increasing non-metallic character upwards down the up to the group, and decreasing metallic character downwards. Means here increasing metallic character. So if you see here, increasing metallic character means down the group. If you see that groups, what, how will you see top to bottom? So it is nothing but down the group. Down the group, metallic character increases. Next, from left to right, across the period, they are given left to right, and for metallic character, right to left, they are given because metallic character increases from right to left, and left to right, non-metallic character increases. Similarly, up the group, here it is up the group, top of the group, up the group, down the group, metallic character, up the group, non-metallic nature. So lithium is less metallic when compared to cesium. Similarly, in case of non-metals, if you take nitrogen, nitrogen is more non-metallic than the last element in that group, that is lead, and so on. So I hope it is clear now. So general trends of the metallic character of an element. Now here all the properties of the elements are given in picture. Clearly you can see this. This is very, very important. So first, if you take atomic radius down the group, atomic radius decreases. The decreasing line means down the group. And electron affinity, if you take from left to right, electron affinity. I'm just highlighting it. You just see here what I'm discussing. I'm highlighting it. Highlighters only. Spot. So if you take this atomic radius first, atomic radius down the group decreases, and atomic radius electron affinity across the period increases. Ionization energy across the period increases. Non-metallic character, it increases across the period, left to right, and metallic character, right to left. And electron affinity up to the group means from down to up. Means here from down to up means electron affinity increases, ionization energy also increases. And atomic radius from left to right, atomic radius decreases, and right to atomic radius decreases, increases. Yeah. So this is the trends of the periodic table. So this table is very, very important, especially made for you to understand clearly. So please note it down. And all the trends of periodic properties they will ask in the examination. With reasons also they will ask. So atomic radius, ionic atomic radius across the period. So left to right it increases atomic radius, and right to left here they have given right to left, so it is decreasing. Down the group decreasing, and increasing arrow, decreasing arrow. We have different arrows. So I hope you can understand clearly. Next property is periodic property is diagonal relationship. This already we discussed, but more detail we will discuss in this. Very important diagonal relationship. So what is diagonal relationship? A diagonal relationship is said to exist between certain pairs adjacent atoms, elements in the second and third pairs. That is first 20 elements only of the periodic table. So what again I'm repeating, a diagonal relationship is said to exist between certain pairs of diagonally adjacent elements. Diagonally adjacent elements means like lithium, magnesium and so on. In the second and third pairs, that too only in second and third pairs, and that too up to atomic numbers 20 only of the periodic table. These pairs are lithium and magnesium. So they have similar properties. Based on that they have diagonally related to each other. Next we have aluminium, beryllium and aluminium. Next we have boron and silicon. So boron and silicon. So these are the elements we have which are diagonally related to each other, exhibit similar properties. For example, boron and silicon forms both semiconductors, forming halides that are hydrolyzed in water and having acidic oxides. So the oxides of silicon and boron are acidic in nature. So they form the oxides of type. So they form the oxides along with oxygen, and they are acidic in nature. So in this way they are having diagonal relationship. What are the main properties? Boron and silicon both forms semiconductors, and they are forming halides that are hydrolyzed in water. Means the halides of boron as well as the halides of silicon are hydrolyzed in water, and they have acidic oxides. They form acidic oxides. Next, the organization of elements on the periodic table in a horizontal rows and vertical columns makes certain relationships more apparent periodic law. So moving rightward and descending the move the pointer, moving rightward and descending the periodic table have opposite effects on atomic radii of isolated atoms. So moving rightward across the period decreases the atomic radii of atoms, while moving down the group will increase the atomic radii. So already we discussed these points. So, and here more important, I told you one more example for diagonal relationship. Lithium and magnesium are diagonal related. So how they are diagonal related? I'll give one example. Lithium combines with air and forms lithium oxide along with lithium nitride, Li3N. Whereas magnesium also combines with air, forms magnesium oxide along with magnesium nitride, Mg3N2. So that's why they are diagonal related to each other. So not only one property, so many properties, and hence they are, as they have similar properties and they are diagonally adjacent elements. So that is why that is the relation called diagonal relationship we got. Similarly, on moving rightward a period, the element becomes progressively more covalent because of non-metallic character. Across the period, what happens? The compounds formed are more covalent, less basic, and more electronegative. Whereas on moving down the group, the elements become more ionic because of metallic character. As metallic character increases, all metals and non-metal combinations forms ionic bond. So they are mostly ionic and more basic and less electronegative. Thus, on both descending a period and crossing a group by one element, changes cancel each other out, and elements with similar properties which have similar chemistry are often found. The atomic size, electronegativity, and properties of the compound of the diagonal members are similar. So why they are diagonal? Because of these points only. They have similar properties. Next. So the main group period to lithium, magnesium, beryllium, aluminium, boron, silicon, carbon, and phosphorus. So these are all diagonal related. So lithium, magnesium, beryllium, and aluminium. And the oxides of lithium oxide is basic in nature, and whereas the oxides of carbon and boron are acidic in nature. Silicon and phosphorus also acidic in nature. So metallic oxides are basic in nature. Non-metallic oxides are acidic in nature. Usually metallic oxides are basic in nature. Non-metallic oxides are acidic in nature. Usually, not all metallic and all non-metallic oxides. Next. So these are the main periodic properties so far we have discussed. Next, we have very important based on this diagonal relationship. It is found that chemistry of first group element often has similarities to the chemistry of second group element, that is third period. Second period and third period element of one column to the right in the periodic table. Thus, chemistry as lithium has similarities to that of magnesium. The chemistry of beryllium is similar to that of aluminium, and the chemistry of boron is similar to that of silicon. The reasons for the existence of diagonal relationships are not fully understood, but charge density is a factor. For example, lithium plus is a small cation with positive charge, and magnesium plus 2 is somewhat larger with a positive charge plus 2. So the ionic potential of each of the two ions is roughly the same. It was revealed by an examination that the charge density of lithium is much closer to the magnesium than that of other alkali metals using lithium magnesium pair under room temperature and pressure. So already I told you, when combined with oxygen under standard conditions, lithium and magnesium only form normal oxides, whereas sodium forms peroxides, and metals below sodium in addition form superoxides. For example, I'll tell you the explanation. Lithium will form lithium oxide, normal oxide. Sodium will form sodium normal oxide along with sodium peroxide. Whereas other elements, that is lithium sodium, after lithium sodium you have potassium. Potassium will form normal oxide, peroxide, as well as superoxide. Superoxide of the type KO2. So potassium will form, rubidium will form, cesium will form. So all other metals in that particular group, they form superoxides. So that is the only difference. Lithium is a only group one element which forms a stable nitride. So as I told you, when combined with air, it combines with oxygen as well as nitrogen, and it forms a compound called lithium nitride. Magnesium as well as other group 2 elements also form nitrides. So magnesium also the same way. Magnesium forms oxides as well as nitrides. So lithium carbonate, next Li2CO3, phosphate and fluoride are sparingly soluble in water. So the carbonates, phosphates and fluorides of lithium are sparingly soluble in water. The corresponding group 2 salts are insoluble. Think lattice and solvation energies. So both lithium and magnesium form covalent organometallic compounds. That is lithium methyl, magnesium methyl, Grignard's reagent. So what is Grignard's reagent? Alkyl magnesium halide. Alkyl magnesium halide is called Grignard's reagent. This Grignard's reagent only you will be knowing in 12th class or even ending of the 11th class. You just listen now. So what is Grignard's reagent? It is a combination of lithium metal or along with methyl group and magnesium metal along with methyl halide group. So methyl and halogens also. So what is Grignard's reagent? Alkyl magnesium halide. Alkyl magnesium halide is called Grignard's reagent. I hope it is clear now. So, and more important, chlorides of both lithium and magnesium are deliquescent, absorbs moisture from surroundings, and soluble in alcohol and pyridine. So lithium chloride, like magnesium chloride also. Lithium chloride, like magnesium chloride also, they form water crystallization. They form the salts of type MgCl2 6H2O, LiCl2 6H2O, 2H2O. So LiCl 2H2O. So lithium carbonate and magnesium carbonate are both unstable and can produce corresponding oxides and carbon dioxide when they are heated. So these are the common chemical properties between lithium and magnesium. Like that you will find the same in case of beryllium and aluminum, and in case of carbon and phosphorus, and in case of boron and silicon. So these are all diagonal relationship. Diagonal relationship means some of the properties of the two elements are mostly similar. That's why it is called diagonal relationship. I hope it is clear now. Next. So solved examples on periodic classification. So I have told you. So based on this periodic classification, you will get trends of periodic properties is most important. So usually you'll get trends. So magnesium has higher melting point of a metal than sodium. Explain. So the melting point of metal depends on the metallic bond strength. Magnesium has stronger metallic bonds due to its smaller size and greater number of valence electrons involved in metallic bonding. So that's why magnesium has melting point greater than sodium. So across the period, the melting point decreases. For up to first it decreases, and after that it increases. Anyway, periodic trends is not there. So only they have compared the magnesium point melting point and sodium melting point. So sodium melting point is obviously low when compared to magnesium. Next question. Among fluorine bond and chlorine bond, so FF bond, Cl bond, which is more stronger and why? So in Cl bond, a filled p orbital of chlorine can overlap with suitable vacant d orbital of adjacent chlorine by thereby introducing some double bond character. So as a double bond is there, bond strength is maximum. So bond strength increases. So this is not possible in fluorine as it has no vacant d orbital. Since fluorine has no vacant d orbital and chlorine has vacant d orbital, because its configuration is 1s2, 2s2, 2p6, 3s2, 3p5. After 3p we have 3d only. That's why it has empty d orbital. So some of the, I'm writing the configuration of chlorine on the board. You can just see here. So chlorine atomic number 17. So its configuration is 1s2, 1s2, 2s2, 2p6, and 3p5. 3s2, 3p5, sorry. 3s2, 3s2, 3p5. So it has valence electrons 3s to 3p5, 7 valence electrons, and 3s, 3p is there. So automatically when 3 is entered, automatically for 3 subshell, we have d orbital also, because 3d we have 3d, but we don't have 2d. So that's why due to the availability of d orbital, some of the electrons of p, when in excited state, goes to d orbital. So due to which what happens, the bond strength becomes more stronger. So Cl bond length is more when compared to Ff bond length because of more bond strength. And fluorine is not possible because the atomic number of fluorine is 9. It has a configuration only 1s2, 2s2, 2p5, 2p5. So for 2 orbital, for 2 orbit, the for principal quantum number 2, we do not have d orbital. But for principal quantum number 3, we have d orbital, that is 3d orbital. So due to the availability of d orbital, the bond strength is maximum in case of Cl single bond Cl, and due to the non-availability of d orbital, the bond strength is less in fluorine molecule. I hope it is clear now. Next question. Second electron affinity for halogens is 0. Explain. Very important question. After addition of one electron in halogen atoms. So what is electron affinity? When a neutral gas atom gains electron, the amount of energy released is called its electron affinity. So if it gains one electron, it is first electron affinity. If it gains two electrons, it is called second electron affinity. In case of chlorine or fluorine, halogens, chlorine, bromine, iodine. Let us see fluorine. 1s2, fluorine 1s2, 2s2, 2p5. So if it gains one electron, then it becomes F minus. F minus configuration, if you see, F minus, because the element which gains electron will get negative charge. So 1s2, 2s2, 2p6, stable. So that's why second electron affinity is not possible because all the electrons are filled in the subshells, that is 1s2, 2s2, 2p6. So after addition of one electron in halogen atom, formation of halide ion takes place, which has fully filled configuration, that is ns2 np6 configuration, and thus possesses no tendency to gain one more electron. That's why the second electron affinity means second electron gaining. So is 0 for halogens. Next question. Sodium hydroxide behaves as a base while zinc hydroxide is amphoteric. Why? See, zinc hydroxide is amphoteric because we have amphoteric oxides. Transition metals are less metallic in character. So when they are less metallic character. Usually metallic oxides form bases and non-metallic oxides are acidic. Whereas less metallic oxides, that is less metallic is like transition metal oxides. There are somehow transition metal oxides are amphoteric in nature. So even aluminum oxide is also amphoteric. What is amphoteric means? It has a tendency to combine with acid and base to form salt and water. So it has a tendency to form it has a tendency to combine with acid as well as base and release hydrogen gas. So that is called amphoteric in nature. So in sodium hydroxide, the bond electronegativity difference between sodium and oxygen. In sodium hydroxide, the bond electronegativity difference between sodium and oxygen is greater than between hydrogen and oxygen, and therefore it is a sodium-oxygen bond that breaks, releasing OH minus. Whereas in the case of zinc hydroxide, the difference of electronegativity of zinc, oxygen, and OH are almost same. So there is equal probability of that bond breaks in both the ways, leading to an amphoteric character. I hope it is clear now. So these solved examples are important because all these are previous competitive questions. Next question. Lithium chloride has lower melting point than sodium chloride. Explain. Since lithium chloride is smaller in size than sodium, already you know lithium cation, sodium is also forming cation. So lithium size, the size of lithium is less when compared to sodium, because as we go down the group, that atomic size increases due to the increasing of number of shells. So in the first case, lithium 1s to 2s1, whereas in second case, sodium it has 1s2, 2s2, 2p6, and 3s1. So the outermost configuration for lithium is 2s1. whereas for sodium it is 3s1. So one more shell is added, that is extra orbit. So it has higher ionization. So lithium chloride is smaller in size and than sodium because it has higher ionization energy. Means if you want to remove the electron from lithium, it is very difficult when compared to sodium because the lithium atom is very small in size, so it has more nuclear attraction. Which has more nuclear attraction? The valence electron of lithium atom has more nuclear attraction. So due to this, what happens? It has larger ionization energy. So therefore, it has greater tendency to form covalent compounds. That's why the compounds, even though lithium is a metal, the compounds have a covalent in nature because they have low melting point, as they have greater tendency to form covalent compounds because of higher ionization energy. So if a compound has higher ionization energy, the element has higher ionization energy, it is having the tendency to form covalent compounds. So lithium chloride, being a covalent compound, has a lower melting point than sodium chloride, which is ionic in nature. So ionic compounds are having higher melting points because they are solids at room temperature, and covalent compounds are having low melting points because they are either liquids or gas at room temperature. So I hope it is clear now. Next question. Why does xenon react with fluorine whereas neon does not? As I already told you, so all noble gases, they are stable. Stable means what? They have completely filled uh, completely full completely filled electrons in the outermost shells. So as they are completely filled electrons in all the orbitals, they are stable and hence they do not take part in chemical reaction. That's why xenon reacts with fluorine and forms xenon difluoride because of the electronegativity or the some because of this reason, that is the ionization enthalpy for xenon is equal to almost oxygen. That's why they have tried it, but neon does not form any compound. So in xenon, the principal quantum number n becomes 5, are much farther from the nucleus than those of neon and much less tightly held by the nucleus. They are more willing to be shared than those in neon. Also, xenon has empty 5d orbitals, which can help to accommodate bonding pairs of electrons, while neon has no valence orbitals filled. All the valence orbitals are filled, so no empty orbital. So that's why neon cannot form with fluorine, whereas xenon can react with fluorine. Next. The electron affinity of fluorine is plus 37 electron volts. They have given the electron affinity value in electron volts. How much energy in kilojoules is released when 3.55 grams of chlorine is converted completely into Cl minus in the gaseous state? So some amount of chlorine is taken and it is converted into chlorine ion. So what is chlorine ion means Cl minus. When the chlorine can form chlorine ion by gaining electron. So in that process, whatever the energy is released, it is called electron gain enthalpy. Electron gain enthalpy or electron affinity both are same. So chlorine gains electron and forms Cl minus and giving out energy of 37 electron volts. So energy released when 1 mole of 35.5 grams of chlorine atom changes completely into Cl minus gives you 37 into 96.49 kilojoules, because for 1 mole of any atom it has number of, that is atoms into atomic weight into 96.49 kilojoules per mole. So it is coming around 357.01 kilojoules. So similar energy released when 3.55 grams of chlorine atoms change completely into Cl minus is also 357.01 by 35.5 into 3.55, which is coming around 35.0701 kilojoules. So this is the answer. So I hope it is clear. Next question. Question number 8. Compare qualitatively. Qualitative means bulkily. The first and second ionization potential of copper and zinc. Explain the observation. So if you take the copper into consideration, its atomic number is 29, whereas zinc its atomic number is 30. So the first IP of Cu is less than that of zinc because copper formation is 3d10 4s1. Outermost configuration of copper is 3d10 4s1. Whereas for zinc it is 3d10 4s2. This is outermost configuration of copper and zinc. First IP of ionization potential of copper is less than that of zinc because removal of one electron from 4s orbital of Cu leaves completely filled d orbitals, and in that of zinc, a completely filled 4s orbital is converted into a half filled orbital. So definitely zinc is having more ionization potential than copper, because the electron should be removed, should be from stable configuration. So that is 3d10 4s2 in case of zinc. So, but in case of second ionization potential, the case is reversed, as Cu plus gives an incomplete filled d orbital, that is 3d10, and zinc ion gives completely filled 3d10 orbital. So we have to see the electronic configuration for answering this type of questions. So that's why electronic configuration in the last chapter we had discussed atomic structure. It is very, very important concept. Next. The electron affinity of sulfur is greater than oxygen. Why? So as we move from left to right, electron affinity value increases, but down the group, electron affinity value decreases. But in case of oxygen and sulfur, why? Because oxygen is in the same group and sulfur is in the same group. So down the group, already we have seen that electron affinity value decreases. But here the electron affinity value of sulfur is greater than oxygen, because this is because smaller size of oxygen, due to which it has got higher higher charge density, and thus electron configuration increases as it takes electron. So its ionization energy or electron affinity is less than sulfur. I hope it is clear now. Next. In S and P block elements, the oxygen state changes by 2 units, but in transition elements, it changes in units of 1. Explain. So this is due to a pair of electrons remaining paired in a OUS form and becoming unpaired in IC form. As I told you, transition elements has variable valency. Higher valency should be taken as IC form, and lower valency should be taken as OUS. For example, iron Fe+2 ferrous. Fe+3 higher oxygen state, it is ferric. Similarly, tin chloride, so tin Sn+2, it is having less, that is OUS, that is stannous chloride. Whereas SnCl4, it is stannous tetrachloride, that is tin tetrachloride, so SnCl4. So it has 4 halogen atoms. So it is called stannic and it is called stannous. So but in transition metals, so tin, phosphorus, technetium, etc. But in transition metals, different number of d orbitals, d electrons may take part in bonding. That is example Fe+2, Fe+3, and Cu+Cu+2. That's why in S and P block elements, the oxygen state changes by 2 units, whereas in transition elements, it changes by only 1 unit. Next. Why is the atomic radius of oxygen slightly more than that of nitrogen? Atomic radius of oxygen, this is also based on electron configuration. If you see, the atomic number of oxygen is 8. So configuration is 1s2, 2s2. Oxygen I'm writing, nitrogen also I'm writing, both we are writing. So oxygen 1s2, 2s2, 2p4. For nitrogen 1s2, because atomic number 7. So 1s2, 2s2, 2p3. So it is half filled. Nitrogen is having half filled, whereas half filled are completely filled orbitals. Whereas oxygen do not have half filled orbitals. They are not completely filled orbitals. It has half filled orbitals. So nitrogen atom has a half filled subshell of 2p3. The next electron is oxygen, enters an occupied p orbital, that is 2p4. So the 2pz orbital has a pair of electrons. The resulting repulsion between this pair of electrons more than offsets the attraction of the increased nuclear charge. So this can be seen from the values of atomic radii given in a table. So as we move from left to right, also you have to carefully observe while writing the periodic trends, because they'll ask in the examination only periodic trends, not any other topic. So for metals, periodic trends; for non-metals, periodic trend is over. Now we are trying to discuss next question. Next question. Which ion is larger in size and why? So as we discussed, in case of charges, atomic sizes or ionic sizes, already for cation, the neutral atom is greater than the cation, its cation, whereas the neutral atom size is lesser than anionic size. Suppose if an element forms cation, so for example, sodium or sodium plus, sodium is having more size than sodium ion, because number of electrons decreases in sodium ion, because after losing one electron. Similarly, in case of sulfur, S2 minus. Sulfur is having lesser atomic size than S2 minus, because S2 minus means gaining 2 more electrons. As it is gaining 2 more electrons, the atomic size increases. As the atomic size increases, ionic size also increases. That's why between cations and anions are bigger than cations. Now between K plus and Cl minus, it is very interesting. So K plus and Cl minus are isoelectronic. As we discussed in the second chapter, what are isoelectronic? Same number of electrons. So K plus contains 18 electrons, Cl minus contains also 18 electrons. That is, they possess 18 electrons. In this case of K plus, there are 19 protons attacking the 18 electrons. While in Cl minus, there are 17 protons only attacking the 18 electrons. Hence, the effective nuclear charge is greater in K plus than Cl minus. Automatically, as the effective nuclear charge increases in K plus, the size decreases. So Cl minus is greater than K plus. Cl minus, the ionic radius, that is Cl minus, is having more size than K plus. Very, very important question. Next question. Question number 13. Beryllium has higher ionization potential than boron. Explain. Very, very important. As we move from left to right, the ionization potential value should decrease, but here it is higher ionization potential than boron because boron is right hand side and left hand side is beryllium. So beryllium is having higher ionization potential again because it has completely filled orbital. So for all ionization potential, for all the periodic properties, especially ionization potential and atomic radius, we have to see the electronic configuration. So electronic configuration we have discussed in the last previous chapter, that is atomic structure. So beryllium has fully filled orbital, that is 1s2 2s2, whereas boron does not have fully filled orbital, that is one. It has the configuration 1s2 2s2 2p1, 1s2 2s2 2p1. Again, s electron is more penetrating compared to p electron. That's why more energy is required to remove electron from 2s orbital compared to 2p orbital. So beryllium has higher ionization energy. Beryllium has higher ionization energy than boron. So I hope it is clear now. So when you are taking about ionization potential and atomic radius, first you have to see the electronic configuration. So half filled and fully filled is there, means definitely they have higher ionization potential and lower atomic radius. Whereas complete filled and half filled, they have higher ionization potential and lower atomic radius. I hope it is clear. Next. The electron affinity of magnesium is negative, while that of chlorine is positive. Account for the observation. Since magnesium is a metal and it has a electron configuration 1s2 2s2 2p6 3s2, it has a tendency to lose electrons in order to attain stable octet configuration. So when an electron is introduced into its outermost shell, energy has to be supplied. So it is an endothermic process, and all electron affinity is exothermic process because electron affinity is assigned a negative value. So chlorine has a electron configuration 1s2 2s2 2p6 3s2 3p5. So it requires one more electron for attaining stability. So it has more electron affinity. So it readily accepts an electron. Hence the electronation process is exothermic and its electron affinity is positive. So if an electron affinity process is endothermic, the electron affinity value becomes negative. And if the electron affinity process is exothermic, it is positive. So in general words, simply you can say magnesium is a metal, so it has a tendency to lose electron, not gain electron. But still, if you give electron to magnesium also, even if it accepts also, what happens here? It is an endothermic process because it is not in a position to take the electron. Whereas chlorine has in a position to take the electron, so it readily accepts the proton. Hence, the electronation process is exothermic and its electron affinity is positive. So, on the whole, what you can understand from this question, if the process of giving electron is endothermic, then the electron affinity value is negative. And if the process of giving electron is exothermic, the electron affinity value is positive. I hope it is clear. So automatically electron affinity of chlorine is more when compared to magnesium. Next. So I hope this is clear. So this is the end of this session. The next session we'll discuss. Regarding the questions of the entire chapter. So next session we are going to do all the chapters. In this session, what we have discussed some more periodic properties. So all the periodic properties is finished. So the explanation part of periodic table, that is periodic classification of elements, is completed. So in the next hour, we'll discuss only the problems related to, that is the questions related for objective orientation. Since the only explanation part is there in this chapter, that's why I have not given after lecture the questions. Now after completing these 3 lectures, we'll give the next lecture, we'll do only questions based on periodic classification. I hope it is clear. Thank you.